Tonight, we embark on a journey that will forever change the way you perceive the universe. Prepare yourself as we dive deep into something that is both mind-boggling and humbling: the boundless emptiness that exists between the stars. You might think you know space, but there is so much more to the cosmos than the stars themselves. Stars are the exceptions, and between them lies something far more fascinating: the vast, infinite emptiness. It's a space so enormous that words struggle to capture its scale. It will make you question everything you think you know about time, distance, and our place in the universe. When we gaze at the night sky, what we're seeing is not just a cluster of stars. No, what we're truly observing are rare pockets of energy, massive explosions of nuclear fire, illuminating the darkness. But the rest? The darkness between those points of light? It is the ocean that surrounds those blazing stars. An ocean so empty that even the most extreme emptiness on Earth would be swallowed up by its nothingness. Imagine you're floating in the middle of this ocean, a place so void that it disrupts our understanding of space itself. We're talking about interstellar space. It isn't just empty, as we imagine. It is a unique environment with its own set of characteristics and properties. Stars are mere dots scattered across this ocean, moments of brilliance and chaos in an otherwise serene and lifeless expanse. And when we start to wrap our minds around these distances, it's almost incomprehensible. For every single light that pierces through this darkness, there's a magnitude of void that dwarfs it. As you see the Milky Way's gleaming band of stars, remember, it's not the stars you're truly seeing. It's the glow of distant islands in an ocean of profound isolation. The stars, indeed, are the rare exceptions. The dark void that stretches across light years is the norm. But there's something even more staggering: the scale of distance. We've all heard the term light year, but how well do we really understand what it means? When light, traveling at a speed of 186,000 miles per second, moves through the vast emptiness of space, it's still finite. A light year, the distance that light can travel in 1 year, is nearly 5.88 trillion miles. Let that number sink in. It is a distance so far that the human mind cannot truly fathom it. Yet, even light takes years to travel across these distances. In fact, it would take light over 4 years to travel from the closest star to Earth, Proxima Centauri. Now, imagine if you were to drive in a car at 70 miles per hour, the average speed of a highway drive. How long would it take to reach Proxima Centauri, that nearby neighbor of ours? 40 million years. Imagine that, driving at 70 miles per hour for 40 million years, and you still wouldn't be there. Every step you took, every hour you passed, every year that unfolded, would be a mere fraction of the vastness that still separates you from your destination. The entire history of humanity, the rise of civilization, and the development of cultures would pass you by while you continued, without stopping, without changing, without a moment of rest. Even our fastest spacecraft, the Parker Solar Probe, traveling at an astonishing 430,000 miles per hour, would take 6,500 years to reach Proxima Centauri. That's still a time frame too large to fathom. So, now let's take a step back and think. How is humanity supposed to traverse these distances? How could any civilization possibly cross this monumental gap in time? These distances challenge everything we know about travel, communication, and survival. They stretch the very notion of time. Time, as we understand it, becomes something altogether alien when we look at the spaces between the stars. A message sent to a distant star would take years, decades, or centuries to receive a reply. Our communication with others, even with the most advanced technologies, would be measured in millennia, not minutes. This isn't science fiction. This is the grim reality we must face. Let's try to make this more tangible. Imagine scaling down the universe to a human level. If the sun were a tiny grain of sand, only 1 millimeter in diameter, How far would the closest star, Proxima Centauri, be? 18 miles. Not 18 inches, not 18 feet, 18 miles. You would hold the sun in one hand and the Earth in the other, just a few inches apart, and then you would walk 18 miles across an empty landscape until you found another grain of sand. That's the space between our sun and the closest star. Even with the best telescopes, our view of the stars is always filtered through these miles and miles of emptiness. We're not looking at a network of stars clustered together. We're looking at a scattering of islands, precious, but surrounded by vast, desolate seas of nothing. The distances between the stars are vast beyond human comprehension. And yet, humanity continues to push forward, reaching for these distant lights. Now that we've covered just a taste of the distances between stars, we can begin to explore what fills this great emptiness. Is it truly empty? Or is there something waiting in the void? That's what we will explore next, as we uncover the strange, invisible forces that occupy the great expanse of interstellar space. As we continue our journey into the unimaginable vastness of interstellar space, it's time to shift our focus. We've established the scale of the distances involved, and we've begun to grasp how truly empty space is between stars. But space isn't completely devoid of matter. It's not an absolute vacuum. Far from it. In this profound emptiness, there is something there, something that fills the gulf between stars, something almost as invisible as the vast void itself. It's called the interstellar medium. You might think of space as empty, but that's a misleading oversimplification. There's more going on out there than we realize. The interstellar medium is the material that exists in the space between stars, and it's primarily composed of gas, dust, and magnetic fields. It might seem like an insignificant detail when compared to the mighty stars, but the interstellar medium is what bridges the cosmic islands and holds the universe together in ways that are hard to imagine. The gas is mostly hydrogen, the simplest and most abundant element in the universe. In fact, hydrogen makes up around 70% of the mass of the interstellar medium. Helium makes up most of the rest, about 28%. The remaining 2% consists of heavier elements, which astronomers call metals, though these metals include elements like carbon, oxygen, and nitrogen. They are all part of the sparse, scattered material floating between the stars, creating a hauntingly thin web that stretches across the galaxy. However, despite its composition, this medium is almost inconceivably sparse. The density of matter in interstellar space is incredibly low. The average density is just about 1 atom per cubic centimeter. That's right, one single atom floating in a cube the size of a sugar cube. To put this in perspective, consider the air you're breathing right now. It contains 25 quintillion molecules per cubic centimeter. The air is dense with matter, bouncing molecules off each other, providing the pressure we feel every moment. By contrast, the interstellar medium has about 1 atom per cubic centimeter, which means it's 25 sexillion times less dense than the air around you. Think about how rarefied that is. It's an emptiness that we can hardly grasp, even with the sharpest of minds. But that doesn't mean space is just a plain, featureless void. Even in this incredible emptiness, the interstellar medium has structure. There are regions where the gas is denser, and others where it's sparser, areas where stars are born and areas that remain completely barren. The interstellar medium isn't just one solid block of empty space. It varies. There are different phases of this medium, and each phase has distinct properties and densities. Some of the densest regions of interstellar space are the molecular clouds. These are cold, dark, and dense regions where hydrogen atoms pair up and form molecular hydrogen. They're the stellar nurseries of the universe. It's here that stars are born. These clouds can be incredibly cold. Temperatures can drop to as low as 10 Kelvin, that's minus 441 degrees Fahrenheit, or minus 263 degrees Celsius, just 10 degrees above absolute zero. In such frigid conditions, hydrogen atoms move very slowly, allowing them to collide and stick together, forming molecules. When these clouds become dense enough, gravity takes over, causing them to collapse. As they collapse, the center of the cloud heats up until it's hot enough for nuclear fusion to begin. This is the birth of a star. The material inside these clouds can be hundreds or even thousands of atoms per cubic centimeter, which, in the context of interstellar space, is quite dense. But when compared to the air we breathe, it's still vastly empty. A single cubic centimeter of air would contain 25 quintillion molecules, more than 1,000 times more than the densest parts of a molecular cloud. While molecular clouds are the birthplace of stars, they're incredibly rare. They make up only 1% of the volume of the interstellar medium. They're the dense, rich pockets that give birth to stars, and, potentially, but most of the interstellar medium is far emptier. As we move beyond the molecular clouds, we enter the cold neutral medium and the warm neutral medium, which are both composed of atomic hydrogen. The cold neutral medium is still made up mostly of hydrogen, but the temperature rises to between 50 and 100 Kelvin, about minus 370 degrees Fahrenheit to minus 280 degrees Fahrenheit. The density in these regions is still very low, typically around 20 to 50 atoms per cubic centimeter. The cold neutral medium makes up about 1 to 5% of the interstellar medium's volume. In contrast, the warm neutral medium consists of hydrogen gas at temperatures of 6,000 to 10,000 Kelvin, roughly 11,000 degrees Fahrenheit to 18,000 degrees Fahrenheit. This is significantly warmer and more diffuse, with densities of only 0.2 to 0.5 atoms per cubic centimeter. This phase accounts for about 10 to 20% of the interstellar medium. The warm neutral medium exists in the form of sheets and filaments, often surrounding molecular clouds, as a transition zone between the densest regions and the sparsest areas beyond. Next comes the warm ionized medium and the hot ionized medium, which are made up of ionized hydrogen atoms that have lost their electrons. These regions are hot, at temperatures around 8,000 Kelvin, about 14,300 degrees Fahrenheit, and have a similar density to the warm neutral medium, about 0.2 to 0.5 atoms per cubic centimeter. But the most dominant phase of the interstellar medium is the hot ionized medium, which fills about 50% to 70% of the interstellar space in our galaxy. This is a plasma, where the gas is so hot that all the hydrogen is completely ionized. The density in this region is incredibly low, just 0.003 atoms per cubic centimeter. This is a plasma heated by supernova explosions, which send shock waves across the space, raising the temperature to millions of degrees. These bubbles of superheated plasma expand and cool, creating vast voids in the interstellar medium. One of the most dangerous and invisible parts of the interstellar medium are the cosmic rays, high-energy particles that travel through space at nearly the speed of light. These cosmic rays are mostly protons, but they can also be heavier atomic nuclei, such as helium, oxygen, and even iron. Cosmic rays are extremely energetic and can be harmful to living organisms. When they collide with atoms in living tissues, they can strip electrons from molecules, causing damage to DNA, cells, and tissues. The danger of cosmic rays is cumulative, meaning that the longer a spacecraft or traveler is exposed to them, the greater the risk. Lastly, there's interstellar dust. These tiny grains, made from silicates, carbon compounds, and in colder regions, water ice, are sparse, about 1 grain for every 100 billion hydrogen atoms. But despite their rarity, they can have a significant impact on spacecraft. Even a tiny dust grain, traveling at extremely high speeds, can cause considerable damage to spacecraft. At the speeds needed for interstellar travel, a dust grain could strike a spacecraft with the force of a small explosion. This creates a risk for any vessel traveling through the vast emptiness, making protection against these tiny, fast-moving particles one of the most significant challenges of interstellar travel. Now that we've come to understand the vastness of interstellar space, its emptiness, and the substances that fill the void, the next natural question arises: how can we possibly cross this seemingly endless expanse? The challenges of traveling through interstellar space are monumental, not just in terms of the distance to be covered, but also the technological, physical, and resource-related hurdles we must overcome. To truly grasp the enormity of these challenges, we need to think about what it takes to travel from one star to another. We've already established that the nearest star to us, Proxima Centauri, is more than 4 light-years away. With our current technology, the fastest spacecraft ever built, Voyager 1, is traveling at a speed of about 38,000 miles per hour, or 61,000 kilometers per hour. Even at this astonishing speed, it would take 73,000 years to reach Proxima Centauri. That means our current fastest spacecraft would still be outpaced by the light it would take to reach the nearest star. Even the most advanced chemical rockets, which could potentially achieve velocities up to 35,000 kilometers per h, 20,000 miles per hour, would take tens of thousands of years to make the journey. The challenge is so vast that the scale of time becomes incomprehensible. Speed. The overwhelming need for revolution, the core problem with our current approach to interstellar travel, is that we simply don't have spacecraft that travel fast enough. To reach other stars within a human lifetime, we need to dramatically change our approach. Our best current speed is nowhere near fast enough to make interstellar travel feasible in a reasonable time frame. The numbers tell us that to reach Proxima Centauri within 50 years, a spacecraft would need to travel at around 10% of the speed of light, a pace that's about 100 times faster than our fastest spacecraft. This is the scale of the problem. We don't need to be just a little bit faster. We need to be exponentially faster by orders of magnitude. Doubling the speed would still result in a journey that would last thousands of years, while even a tenfold increase would only reduce the journey to centuries, still an unacceptably long time. Reaching even 1% of the speed of light would represent a massive technological leap. Currently, we're nowhere near this threshold, but the dream of reaching a fraction of light speed isn't as out of reach as it might seem. The question is, how can we achieve this? Propulsion methods. Thinking beyond the limits at the moment, we rely on chemical propulsion for space travel. These rockets work by expelling fuel at high speed to generate thrust, but the energy required to reach the speeds needed for interstellar travel using chemical propulsion would be absolutely astronomical, literally. And even if we could develop these systems, we would run into fuel limitations. There is simply not enough fuel that can fit on a spacecraft for it to reach another star, let alone return. This is why we need new methods. Let's look at the potential alternatives. Some are theoretical, while others are already being researched. Some of these methods might one day make interstellar travel a reality, though there's still much work to be done. 1. Solar sails, harnessing the power of the sun. One of the most promising concepts for interstellar propulsion is the idea of solar sails. Solar sails use light pressure to propel spacecraft. While the idea is simple in concept, the technology could allow for long-term acceleration without needing any fuel. Instead of traditional rockets, solar sails would unfurl a massive reflective sail, which would be pushed along by photons emitted from a star, including our own sun. This pressure would cause the spacecraft to accelerate gradually over time. The advantage of solar sails is that they require no fuel. They can accelerate continuously without needing to carry any propellant. However, there's a limitation. The farther a spacecraft travels from its star, the weaker the pressure becomes. This means that solar sails would work efficiently only within a limited range. Far beyond that, they wouldn't generate enough thrust to make interstellar travel viable. Even with the limits, solar sails are extremely promising for short-range missions. But interstellar journeys will require more power than a simple sail can collect, especially if the spacecraft is far from a star. The next step in this technology is what's called Breakthrough Starshot, a mission to send tiny spacecraft to another star using powerful lasers. 2. Breakthrough Starshot, laser-powered exploration. In 2016, physicist Yuri Milner and Stephen Hawking introduced an ambitious concept called Breakthrough Starshot. The idea is to use powerful ground-based lasers to accelerate a tiny spacecraft, about the size of a laptop chip, to 20% of the speed of light. With this incredible velocity, the spacecraft would take just 20 years to reach Proxima Centauri. The spacecraft, known as a star chip, would carry camera and communication equipment and would be propelled by a light sail that would reflect the lasers beamed from Earth. The craft would be small, lightweight, and cost-efficient. Its total mass would be about 1 gram, and the sail itself would be no more than a few microns thick. This technology holds tremendous potential, but there are numerous engineering challenges. We're talking about building laser arrays that could produce hundreds of gigawatts of energy, tracking tiny spacecraft across light years, and dealing with the extreme space radiation that would bombard the spacecraft during its voyage. But despite these challenges, Breakthrough Starshot represents one of the most credible paths to interstellar travel in the near future. 3. Nuclear propulsion, the power of the atom. Another potential propulsion technology that could one day make interstellar travel possible is nuclear propulsion. Nuclear-powered spacecraft are already being used in space exploration to provide energy to spacecraft in deep space. But when it comes to interstellar travel, we need more raw power. Nuclear fusion, the same process that powers the sun, could provide an enormous boost. One of the most notable programs exploring nuclear propulsion is Project Orion. In the 1960s, scientists proposed using nuclear explosions to propel spacecraft forward. The spacecraft would use the shockwaves of nuclear detonations to push a large pusher plate to accelerate the spacecraft. While Project Orion was never realized due to political and environmental concerns, nuclear propulsion still holds promise for high-speed interstellar travel. It offers potential speeds of 5% of the speed of light, which would reduce travel time to Proxima Centauri to around 80 to 140 years, a more manageable time frame, though still longer than a human lifetime. 4. Antimatter propulsion. The ultimate efficiency, perhaps the most exciting, though still theoretical, propulsion technology is antimatter propulsion. The basic principle behind antimatter propulsion is simple. When matter and antimatter collide, they annihilate each other completely, converting their entire mass into energy. This 100% efficiency makes antimatter an incredible potential fuel source for interstellar travel. In theory, spacecraft powered by antimatter could reach a significant fraction of the speed of light. However, antimatter is incredibly difficult to produce. Currently, we've only produced minute quantities, and it would take billions of dollars to generate enough antimatter to fuel a spacecraft. Despite the challenges, antimatter propulsion remains one of the most fascinating possibilities for future exploration. If we can overcome the technological barriers to producing and storing antimatter, we may one day achieve high-speed interstellar travel. As we continue this journey into the future of humanity and the cosmos, we must confront some fundamental questions. What will our species look like when we are no longer confined to Earth? What would it take for us to leave behind the planet that has sustained us for so long and venture into the vast unknown of interstellar space? The challenges of interstellar travel are immense, but the potential for what lies beyond is equally vast. We have seen that interstellar distances are truly beyond our comprehension, even with our most advanced technologies. Yet the idea of humanity spreading across the stars remains one of the most profound aspirations of our species. But as we start considering what it takes to make this leap, we must recognize that the obstacles are not only technological. Psychological, ethical, and social challenges are just as significant in shaping the future of human civilization beyond Earth. Imagine a generation ship, a vessel designed to house humans for centuries, maybe even millennia, while they travel from one star to another. Those who embark on this journey would never return to Earth. Instead, they would live and die aboard this ship, passing on the mission to their descendants. The idea is simple in theory, but the reality of life aboard such a ship is far more complex and uncertain. The people on board would face profound social isolation, not just from Earth, but from all other human civilizations. The spacecraft itself would need to be a self-sustaining system, able to produce food, water, and oxygen for its inhabitants for the entire duration of their lives. And beyond life support, the crew would need to find ways to preserve their mental and emotional well-being in an environment that feels more like a closed, unchanging world than a journey toward a new one. The long-term isolation would come with severe psychological implications. Humans are social creatures, and the pressure of being confined to a single space for generations could strain relationships, lead to emotional breakdowns, and introduce conflict between different factions. Psychological health would become just as important as physical survival on these voyages, and the mental challenges of knowing that you are cut off from the rest of humanity, with no hope of returning to Earth, could lead to a form of existential loneliness. As the generations pass, the descendants aboard these ships would likely create their own unique societies and cultures, influenced by the isolation, the environment of their spacecraft, and the need for survival. Over time, they would become a distinct culture, one that might no longer recognize Earth as its home, but instead see itself as a unique civilization. Their language, customs, and even physical adaptations to their environment could evolve in ways that would make them fundamentally different from those who remain on Earth. Social divergence would likely occur over many generations, with no direct connection to the world they once called home. The sense of isolation would deepen as the ship travels farther and farther from Earth. Imagine living in a small, self-contained world where every day is marked by routine and uncertainty. Even the advances in technology that could make long-term space travel possible wouldn't eliminate the human need for connection, companionship, and hope. The closer the crew gets to distant stars, the more they might feel as though they're losing their connection to everything they once knew, everything that made them human. The idea of returning home would become a faded dream for generations aboard these vessels. The moral implications of such a journey are staggering. Should humanity build these ships and send people on journeys with no possibility of return? Should we commit resources to the endeavor, especially when there are so many problems that remain unsolved on Earth? The decision to send people on these interstellar voyages would be fraught with ethical dilemmas. Can we justify sending people into isolation for lifetimes, even for a cause as noble as the expansion of the human species? These questions will become increasingly important as we contemplate our future beyond the solar system. In addition to the psychological impact of such isolation, the crew of any interstellar ship would need to ensure that the ship's systems function continuously. From food production to waste recycling, everything would need to be perfectly balanced to ensure survival. Failure of a single system could lead to catastrophic consequences. And unlike Earth, where help and resupply are just a call away, on a spacecraft, any mistake could be deadly. The technological complexity of maintaining such a system would be enormous. This is not just about creating a ship that moves across the stars. It's about creating a self-sustaining society that will function on its own for hundreds of years, far beyond the lifetimes of its creators. Further complicating matters is the genetic diversity of the crew. A population confined to a spacecraft for centuries may face issues with inbreeding as the gene pool becomes smaller over time. Ensuring genetic health and diversity would become a critical concern, and the crew would need to find innovative ways to mitigate the risks of genetic degeneration. This might include genetic engineering or cryopreservation, but those options come with their own set of ethical issues. Interstellar communication, the barrier of time. One of the greatest challenges for humanity's future in the stars would be communication. As interstellar distances increase, communication with Earth would become progressively more difficult. The speed of light limits how quickly messages can travel across space. Radio signals sent from a spacecraft traveling to Proxima Centauri would take over 4 years to reach Earth. So, if there was an emergency or a question that required assistance, the delay would be incomprehensible. And even with the most advanced communication technology, that time lag would remain a significant barrier. Real-time communication with Earth would become an impossibility, and remote collaboration with home would become a distant memory. As the spacecraft ventures farther from Earth, the messages will take longer and longer to reach their destination. What happens when a civilization is not just distant in space, but in time? Each message, each communication, would be not just from another location, but from another era. A spacecraft might send a message home, but by the time Earth receives it, the people aboard might have changed irrevocably. The isolation imposed by interstellar space could create entirely self-contained civilizations that are, for all intents and purposes, beyond the reach of Earth. Even though humanity would be spread across the stars, these isolated colonies may never truly be able to interact or share information across the great distances that separate them. The path forward, colonizing the cosmos. While these challenges seem daunting, they are not insurmountable. Humanity has always faced seemingly impossible odds. The vision of a human presence on other worlds has inspired generations of scientists, engineers, and dreamers. The technology is still being developed, but the dream of becoming a multistellar species could change the course of human history forever. There are proposals, such as solar sails and nuclear propulsion, that could enable us to reach far-off stars. These technologies offer a glimmer of hope, but they come with their own challenges, many of which we have yet to overcome. However, the more we dream, the more we innovate. Eventually, one way or another, humanity will have to confront the decision of whether we will become a multistellar species or remain a one-planet civilization, vulnerable to the dangers of Earthbound existence. We must decide if we're ready to face the challenges of interstellar life. Are we willing to endure the isolation, the moral dilemmas, and the technological struggles that come with it? Or will we choose to focus our efforts here, on Earth, and continue exploring the solar system instead? The void between the stars may be immense, but so too is humanity's capacity for wonder and resilience. The next chapter of our future may not be written on Earth at all, but in the endless night of interstellar space. As humanity stands on the precipice of a new era, one question looms larger than all the others. Can we overcome the enormous challenges that interstellar travel presents? It's a question we must answer not just for ourselves, but for the future of our species. If we are to expand beyond our solar system to become a truly multistellar civilization, we must push the boundaries of technology, engineering, and even human endurance. Yet, as we look at the technologies currently available to us, the path forward seems uncertain. But uncertainty has never stopped humanity before. In the last few parts, we've explored the daunting distances, the vast emptiness of space, and the deep isolation that will come with venturing to other stars. But technology has always evolved in ways that defy our expectations. Perhaps, just as we once thought flying across oceans would be impossible, there are breakthroughs on the horizon that will allow us to navigate the unimaginable distances of the cosmos. To start, let's examine the most basic but essential concept of propulsion. Even with the knowledge we have today, our fastest spacecraft would take tens of thousands of years to reach the nearest star, Proxima Centauri. At these speeds, light years become more than just measurements of distance. They become merely incomprehensible spans of time. But what if we could drastically improve the speed at which we travel? What if we could harness methods of propulsion that are only now emerging in theoretical discussions? One promising approach is the concept of solar sails. This idea uses the pressure exerted by sunlight to push a spacecraft forward. Although this technology is still in its early stages, it has been successfully demonstrated in small-scale tests. A spacecraft outfitted with a massive, lightweight sail could, theoretically, travel to the stars using nothing more than the sunlight streaming from our sun. The beauty of this system lies in its simplicity. No fuel is required. The spacecraft would simply unfurl its sail, and sunlight would gradually push it onward, accelerating it over time. But solar sails, though promising, have limitations. As a spacecraft travels farther from the sun, the pressure of sunlight diminishes, and the acceleration slows. The challenge then becomes finding a way to sustain this propulsion across vast distances, far beyond the solar system. That's where the concept of using powerful lasers comes into play. Imagine a network of ground-based lasers capable of focusing intense beams of energy on a spacecraft's sail, providing continuous propulsion even when it's far from the sun. This idea, known as breakthrough starshot, has the potential to reach speeds of up to 20% of the speed of light, a truly revolutionary step in human space travel. Yet even these advancements bring their own set of challenges. To propel a spacecraft to 20% of light speed would require an incredible amount of energy. A laser array capable of accelerating a tiny, lightweight spacecraft to such speeds would require more power than the entire world currently consumes. The precision needed to aim these lasers at a spacecraft traveling at tens of thousands of miles per second is another hurdle. Even if we were able to design and construct such a system, there are still immense risks. The spacecraft would be moving so fast that any collision with even a tiny particle of dust or debris could be catastrophic. At those speeds, a single grain of sand could destroy the entire mission. In addition to propulsion, the spacecraft would need to be able to handle the harsh conditions of space travel. As we've discussed, the interstellar medium, while sparse, still contains harmful particles like cosmic rays and interstellar dust. Exposure to cosmic radiation can damage DNA, increase the risk of cancer, and even cause mental and physical degradation over time. The spacecraft would need to be shielded against this radiation, and that shielding must be lightweight and effective. Additionally, interstellar dust, though sparse, could become a significant threat as a spacecraft accelerates to faster and faster speeds. At velocities even a fraction of light speed, collisions with dust particles could be devastating, turning tiny grains into powerful projectiles capable of puncturing the spacecraft or damaging its delicate systems. These challenges don't end with propulsion or shielding. One of the greatest obstacles to long-duration missions is the human element. Any interstellar journey, even with the fastest propulsion systems, would require decades or centuries of travel. How would a human crew cope with the isolation, the psychological strain, and the physical toll of spending their entire lives in a confined, artificial environment? For a journey to a nearby star, such as Proxima Centauri, the travel time would likely exceed a human lifetime. And yet, for humans to venture beyond the solar system, there is no alternative. They would need to face immense psychological and physiological challenges in ways we are only just beginning to understand. The isolation of space travel would have profound effects on the crew. Even with advanced communication systems, the time delay between Earth and the spacecraft would ensure that any communication, any help, would be years or decades away. This isolation could lead to mental health issues, from depression and anxiety to more severe conditions like space-induced paranoia or social breakdown. And it wouldn't just be the astronauts who would suffer. Any colony established on another star system would face the same distant relationship with Earth, leading to generations of separation. It's clear that the technical and human challenges are immense. But even with all these obstacles, the dream of reaching the stars remains an inherent part of humanity's identity. We've always been explorers. Our entire existence is defined by the search for knowledge and the drive to understand the universe around us. Whether it's exploring the surface of the moon, venturing to Mars, or one day stepping onto a distant planet orbiting another sun, our capacity for wonder will propel us forward, even in the face of daunting odds. Ultimately, though, we must recognize that we are not just tackling engineering problems. The desire to explore the stars is bound up in something far deeper: our search for meaning and purpose in an overwhelmingly vast and indifferent universe. To venture beyond our home world is not just about survival. It's about ensuring that humanity's curiosity, our need to ask questions, and our desire to seek out answers will continue, no matter where we go. Even as the technological challenges loom large, it is our collective will to overcome them that will determine whether the dream of interstellar travel becomes a reality. So, where do we go from here? Can we build a spacecraft that will carry humans across the stars? It's too early to say for sure, but one thing is certain: the journey has already begun. With every new breakthrough in technology, every new mission to explore the unknown, we are taking another step toward that distant goal. As we continue to look toward the stars, we find ourselves faced with a future that seems both incredibly hopeful and terrifying. Humanity's fate may be intertwined with the vast void of space, but the human drive to explore will continue to push us to dream and to reach for the impossible. The stars are calling. The question is, are we ready to answer? As we dive deeper into the reality of space exploration, it's important to recognize that interstellar travel is not just about reaching another star. It's also about developing an entirely new way of thinking and approaching the universe. It's not just a technological challenge. It's a challenge to our entire understanding of life, humanity, and our place in the cosmos. The difficulties we face are so vast, so unprecedented, that they force us to rethink everything we know about survival, technology, and the nature of exploration. We've talked a lot about propulsion, radiation, and human resilience, but there is another issue we must confront: time. The time it takes to travel to another star, the time we'll have to endure isolation, and the time needed to develop new technologies that will make interstellar travel possible. Time is the one element that we cannot change, manipulate, or overcome. It is the one constant in space, and it's the one factor that poses the biggest challenge to us as we venture beyond our solar system. Take, for example, the voyages of spacecraft that we have already sent out beyond the solar system, like Voyager 1. Launched in 1977, Voyager 1 is humanity's most distant emissary, currently traveling over 15 billion miles from Earth. Despite being on an incredible journey, Voyager 1 will take over 73,000 years to reach Proxima Centauri, our closest stellar neighbor. In fact, Voyager 1 won't even come close to reaching its target in any meaningful time frame. It will simply pass through the space near Proxima Centauri without slowing down. At the speeds it's traveling, it's merely an artifact of a distant past, one that will be swallowed by time and space long before it gets to its destination. This vast distance problem is not something that we can simply solve with better propulsion or by moving faster. No matter how fast we go, the timescales involved in interstellar travel will be so great that it becomes almost impossible to conceive of a journey where humans can actually make the trip in their lifetime. And that's assuming that interstellar travel itself even becomes viable. After all, we are still facing the technological limitations of space travel, limited by energy and propulsion technologies. Let's pause for a moment and reflect on just how different things are when we shift from our experience on Earth to the realities of space travel. On Earth, time is measured in years, months, days, even seconds. But out in the depths of space, years become eons, and days become millennia. It's easy to think of a year as a short period of time when you're on Earth, but in the vast emptiness of space, a year means very little when compared to the distances that separate stars. When we think of light years, we realize that a year is just the beginning of how much time it would take to travel between stars. Now imagine being part of a spacecraft that's been traveling for hundreds of years, crossing these immense distances between stars. The world you left behind, Earth, will be completely different by the time you arrive at your destination. If you're traveling to Proxima Centauri, for instance, the journey would take decades. By the time you get there, Earth would have undergone radical changes. Technologies would have evolved, societies would have shifted, and the people you left behind would have long since passed. You, or perhaps your descendants, would be the sole representatives of an Earth that no longer exists as you remember it. You would arrive at your destination disconnected, not just from Earth, but from any meaningful connection to the past. This isn't a theoretical idea. This is the reality of interstellar travel. The longevity of a trip, even to the closest stars, presents its own psychological and social challenges. Imagine spending decades or centuries in a confined, isolated spacecraft with no real contact with the home world. The psychological toll of such a journey is unimaginable. How would we maintain mental health, let alone social cohesion, over such long periods? With no guarantee of success or safe arrival, the crew would need to operate autonomously, handling not just technical problems, but also psychological ones. The risk of space madness, isolation, stress, and anxiety would be intense. The human element would need to be prepared for such an incredibly long and solitary journey. We've spoken about the technologies that might get us to the stars. Let's now think about the life that would exist aboard such spacecraft. Would it be possible to sustain life over such long periods? How would humans cope with the incredibly long timelines required for a mission to another star? It's not just about technology, it's about life itself. This brings us to the concept of a generation ship, a massive, self-sustaining spacecraft capable of carrying a population of people for many generations as they travel through space. Generation ships are, in theory, the solution to the problem of long-term space travel. They're ships designed to allow humans to live, work, and reproduce during the course of their interstellar journey. The inhabitants of these ships would live their entire lives aboard, never knowing Earth and never seeing their destination. The ship would essentially be a small, self-contained society, but building such a ship would be an extraordinary challenge. It's not just about technology. There's a whole range of issues to consider: sociological, psychological, biological, and environmental. For one, life support systems would need to be near perfect, recycling air, water, and food. There would need to be medical facilities to handle everything from routine care to unforeseen emergencies. Social structures would need to be created and maintained over multiple generations. How would a society function after generations of isolation? What kind of culture would develop in such a confined, self-contained environment? And perhaps most challenging of all, how would we maintain the biological diversity necessary to prevent inbreeding? And how would we ensure that humanity can thrive in such a closed system? This is not a theoretical question, but a biological imperative. To survive a journey lasting hundreds of years, we would need to ensure that the genetic pool remains sustainable and adaptable, even without fresh input from Earth's population. There are also questions about how to maintain the ship itself. Everything breaks down eventually. Technological malfunctions, equipment failures, and wear and tear would be inevitable. Crew members would need to become skilled engineers, medical experts, and scientists because there would be no chance of receiving help from Earth. There's no emergency rescue mission to send. Everything needed for survival, repair, and progress would need to be available aboard the spacecraft. Would humanity, faced with these immense challenges, be able to keep the dream of interstellar travel alive? While these problems may seem overwhelming, they are not beyond us. With the incredible pace of technological advancement and our deep-rooted spirit of exploration, we may find ways to make long-term interstellar travel a reality. But to do so, we must overcome obstacles, both technological and human. These obstacles will force us to grow, adapt, and change in ways that we cannot yet predict. And while we may not have all the answers today, each step forward brings us closer to the stars, bringing us one step closer to realizing the dream of reaching other worlds. As we continue our exploration into the unknown, we are reminded of just how vast and profound the journey is. There are no easy answers, no shortcuts, no simple solutions. But with every discovery, every failure, and every success, humanity inches closer to its greatest achievement, becoming a multistellar species. The challenges may be great, but they are not insurmountable. As we continue our journey into the unknown depths of interstellar space, it's crucial to recognize the enormity of what we're facing. Space isn't just an empty void between stars. It's a complex, dynamic environment filled with countless dangers, mysteries, and complexities. In addition to the challenges of technology, human endurance, and vast distances, there's one more critical factor we must consider: the potential hazards of interstellar space itself. We've already touched on some of the invisible dangers, such as cosmic rays and interstellar dust, but the deeper we go into space, the more we realize just how many unpredictable forces are at play. Imagine a spacecraft gliding through the darkness, navigating the vast expanses between stars. The crew is isolated, cut off from Earth, entirely dependent on the systems aboard their vessel. But beyond just the technological challenges, the environment they're traveling through presents new, hidden risks that are far more difficult to anticipate. One of the most insidious and dangerous forces at play in interstellar space is magnetic fields. While the magnetic fields of our solar system are relatively well understood, the magnetic fields in interstellar space are a whole different beast. These fields are weak, yet they stretch across vast distances, and they are anything but uniform. The galactic magnetic field permeates the entire Milky Way galaxy, influencing the behavior of charged particles, including cosmic rays and plasma. This magnetic field is not static. It fluctuates and changes, creating irregularities that can cause unpredictable effects on spacecraft traveling through it. For example, one of the proposed methods for interstellar propulsion involves using magnetic fields to manipulate charged particles, such as in a magnetic sail. In theory, such technology could be used to propel spacecraft across interstellar distances by harnessing the power of the galaxy's magnetic field. However, the irregularity and turbulence of these magnetic fields make this kind of propulsion challenging to control. Even small fluctuations in the magnetic field could cause severe navigation problems, potentially leading the spacecraft off course or causing it to lose momentum. And this is just one of the many ways in which interstellar space can throw unexpected challenges at any spacecraft. Solar winds are another phenomenon that we must contend with as we venture further into the galaxy. In our solar system, the sun emits a continuous stream of charged particles known as the solar wind. While this solar wind creates the heliosphere, a protective bubble that shields Earth from many of the dangers of space, it becomes much less powerful as we move beyond our solar system. This means that as a spacecraft travels through interstellar space, it will no longer benefit from the protection of the solar wind. The spacecraft will be exposed to the raw, unfiltered cosmic radiation of deep space, radiation from faraway stars, supernovae, and other galactic events. Cosmic rays are not just a theoretical concern. They are a real, immediate danger. These high-energy particles, often originating from supernova explosions, are capable of penetrating spacecraft shielding, damaging electronic systems, and even causing health problems for astronauts. The human body, while resilient, is not equipped to handle the constant bombardment of cosmic radiation over the course of an interstellar journey. Prolonged exposure could lead to radiation sickness, cancer, or even genetic damage. For long-term missions, ensuring adequate shielding from cosmic radiation will be critical, but this shielding presents its own set of challenges. The vast emptiness of interstellar space, while seemingly calm and quiet, is in reality filled with more radiation, particles, and forces than we might initially think. The technological systems required to protect against these threats are immense, but they come with their own trade-offs. The massive shielding adds weight to the spacecraft, requiring more fuel and energy to keep the ship moving. The materials we use for shielding must also be durable enough to withstand the continuous barrage of cosmic particles over the course of many years, or even centuries. In addition to the challenges posed by radiation, there is the problem of space dust. Though we often imagine space as a vast emptiness, it is far from it. Space is filled with tiny particles of dust, as well as larger objects that could pose significant threats to spacecraft traveling at high speeds. When you're moving at a significant fraction of light speed, even a tiny dust grain can become a dangerous projectile. At speeds greater than 1% of the speed of light, space dust, although sparse, could have devastating impacts on the spacecraft. A tiny grain of dust, moving at these incredible velocities, could collide with the spacecraft with the energy of an explosive force. While a spacecraft might seem immune to the threat of small particles at low speeds, the equation changes dramatically as we approach significant fractions of light speed. A collision with even the smallest dust particle could puncture the outer layers of the spacecraft, causing catastrophic damage to its systems. At present, most spacecraft are designed to endure impacts from micrometeorites and other debris in space, but interstellar dust, moving at much higher speeds, presents a different level of danger. To withstand these impacts, spacecraft would need to employ advanced shielding capable of absorbing and diffusing the energy of high-speed particles. The technology to build such robust shielding is still in its infancy, and developing it will require significant breakthroughs in materials science and engineering. But perhaps one of the most fascinating and yet terrifying aspects of interstellar space is the unpredictability of it all. While we can study cosmic phenomena, simulate conditions, and predict the behaviors of radiation, dust, and magnetic fields, there is no way to know for sure what we'll encounter as we travel beyond our solar system. In many ways, space is an environment where the unexpected reigns. Even with all of our technological advancements, we can only prepare for so much. The true dangers of deep space lie not just in the known threats, but in those we don't even know about yet. As we venture further into the vast unknown, we will discover more about the forces that shape the universe, and about how little we really know about the true nature of interstellar space. This unpredictability extends not just to the environment, but also to the technological challenges of space travel. As we build spacecraft capable of long-duration missions to other stars, we will encounter new technical issues that haven't been thought of yet. The demands of traveling at high velocities for centuries will push the limits of what we can achieve with our current propulsion systems. Spacecraft will need to be self-sustaining, capable of generating power, producing food, recycling air and water, and ensuring the health of the crew for the duration of their journey. These requirements place an incredible strain on existing technologies and force us to think about space travel in ways we never have before. So, as we embark on this quest to reach the stars, we face not just the technological difficulties of building spacecraft that can travel beyond our solar system, but the deep, philosophical questions of human resilience, mental health, and survival. The challenges of interstellar space are not just engineering problems, they are human problems. They will test our spirit, our resolve, and our very definition of what it means to be human. The void between stars is vast, but within it lies the greatest opportunity for exploration and discovery humanity has ever known. As we venture deeper into this unknown, we will inevitably confront the limitations of our current knowledge and technologies. But every step forward will bring us closer to understanding the true nature of the universe and our place within it. As we reach the final part of our journey through the vast and nearly incomprehensible expanse of interstellar space, it's time to reflect on what we've learned. The journey through this vast void, the ocean between stars, is not just about exploring new worlds or reaching distant stars. It's about understanding our place in the universe, confronting the limits of our technology, and realizing just how small and fragile we are in the grand cosmic scheme. We've spent hours exploring the physical properties of space, the dark, cold, and empty regions between stars. We've talked about the difficulties in crossing these distances, the challenges posed by radiation, magnetic fields, dust, and cosmic rays. We've discussed the terrifying vastness of the space between stars and the reality that even the fastest spacecraft we've ever built could take thousands of years to reach the nearest star systems. These are not just numbers. They are barriers that define the future of humanity in space. But perhaps the most profound takeaway from this journey is the realization that we, as a species, are not separate from the cosmos. We are intrinsically connected to the very universe we are striving to understand. Every atom that makes up your body was forged in the hearts of ancient stars. The stardust that forms you, the air you breathe, the food you eat, it all connects us to the universe. You are part of the vast cosmic web that spans across light years, though we are still so small in comparison to the scale of the universe. The night sky, with its twinkling points of light, isn't just a beautiful backdrop for our dreams. It's a constant reminder of our smallness, but also of our remarkable curiosity. We may live on a small planet, orbiting a relatively average star in a galaxy among billions, but we are aware. We can look at the stars and wonder, question, and dream. That is what sets us apart in this immense, indifferent universe. The technological challenges of interstellar travel are immense. We've only scratched the surface of what might be required to travel the vast distances between the stars. The limits of propulsion, shielding, and life support systems make such journeys seem insurmountable, but that hasn't stopped us from dreaming. If anything, it's our dreams, our desire to push beyond the boundaries of what's possible, that will ultimately fuel the advances we need. Innovation, after all, has always been driven by the need to explore the unknown, to face the impossible and say, let's try anyway. Interstellar space, however, remains a realm where human beings would be forced to confront isolation on an unimaginable scale. The loneliness of deep space would be absolute. In the vast emptiness, the absence of sound, light, and matter would echo in ways we cannot truly comprehend until we are there. Spacecraft would be completely self-sustaining, as any reliance on outside help would be impossible. Crews would need to become their own community, isolated not just physically but also from the rest of humanity. Every decision would have to be made independently, with no possibility of external guidance or support. Self-reliance would become the cornerstone of interstellar travel. This isolation, however, is not a permanent state. It's a part of the journey, a phase of our species' exploration. We may never make casual visits to distant stars or communicate with extraterrestrial civilizations in real time, but we will reach new frontiers. We will stretch the boundaries of what is possible, and in doing so, create the framework for future generations to continue the journey. This is not the end, it's just the beginning. The truth of the matter is that humanity, as a species, has always sought to go further. From the first explorers who sailed across uncharted oceans to the astronauts who set foot on the moon, we have been driven by a need to explore, to discover, to understand what lies beyond the horizon. The stars, those distant, unreachable points of light, have always called to us. They are the ultimate frontier, beckoning us to reach beyond the known and venture into the great unknown. But this journey isn't just about the stars or the technology. It's about the human spirit, our curiosity, our resilience, and our ability to adapt. Every step we take toward exploring the cosmos is a reflection of our desire to understand the universe and our place within it. As we stand on the precipice of the unknown, we must remember that we are not just traveling through space, we are traveling through time. The choices we make today will affect the future of humanity and the generations that will follow in our footsteps. In the end, the universe doesn't care whether we reach the stars. It doesn't care whether we live or die thrive, or falter. The cosmos is indifferent, but we, as humans, care deeply. We care about exploring the vastness of space, understanding the mysteries of the universe, and leaving our mark on the cosmos. That, in itself, makes us extraordinary. So, as we close this chapter of our journey, remember this: the stars are far away, but they are not unreachable. The void is vast, but it is not impassable. The emptiness of space is terrifying, but it is also filled with endless possibilities. And even though we may never see the stars in person, even though the distances may forever keep us apart, we are still part of the universe. Every time we look up at the night sky, we are participating in the cosmos, reaching out across light years, touching the stars through our curiosity, our ambition, and our wonder. The journey to the stars may be long, and it may be fraught with challenges and obstacles, but it is a journey we will undertake. The void awaits, and we, with our unrelenting curiosity, will continue to explore it, dream of it, and eventually conquer it. The stars are not as distant as they seem. They live within us. We are already reaching for them in our thoughts, our dreams, and our actions. Thank you for joining me on this journey. The stars will always be there, waiting for us to come, and maybe, just maybe, we will reach them one day. Good night.